Welcome to the deep dive. Today, we're taking that big step from just running a network to really understanding its foundations, the design choices behind it all. We're shifting gears from, troubleshooting someone else's plan to the core design thinking for IPv4 addressing and subnetting. Our goal today, clarity. We want to unpack the why. Why these addresses? Why this structure? So we'll tackle basically 3 key questions for you. What addresses can you actually use? Which ones should you choose? And maybe most practically, what can an existing setup tell you about the network's whole architecture?
Yeah, that last one is, well, it's everything, isn't it? Design isn't just theory on paper. It's the blueprint written right there in the IP addresses. If you're monitoring or troubleshooting some weird slowdown or, adding a new switch or server, you absolutely need to understand the original design intent. It's not just what IP do I pick. It's more like, why did they set it up this way? The answers tell you so much about scale, priorities, maybe even future plans.
Okay, let's get a picture of this. Imagine, the source used this great analogy of a giant sandwich, right? Like kilometers long. Just one massive, completely unmanageable thing. A big Class A network can feel like that, maybe. Subnetting, then, is just, it's the process of taking that huge network and slicing it, chopping it into smaller, more practical, usable pieces. We call those pieces subnets.
Exactly. So a network like, say, 172.16.0.0, that's just the definition. A range of sequential numbers. A subnet is simply a subset of that, like 172.16.10 could be one piece.
For the finance team.
Yeah, or 172.16.2.0 for marketing. Yeah. You're bringing order to the chaos, basically. And this order is absolutely vital for routing to work properly. There are like 2 fundamental rules here.
Yeah.
Addresses within the same subnet. They're never separated by a router. They talk directly. But addresses in different subnets, they have to be separated by at least one router.
Okay, so it's kind of like postal codes, maybe? If you're in the same town, same code, the local mail carrier handles it, different town, different code. It's got to go through the main sorting office, the router, to get rerouted.
Perfect analogy. And the router itself, it's a boundary marker. It connects different networks, different subnets, which means critically, each interface on that router needs its own IP address.
Right.
From the specific subnet it's connected to.
Okay, so we get the basic idea. Now the engineer has to plan. Before even thinking about addresses, there are these 4 questions you need to answer. First, which devices, which hosts actually belong together in the same group? Second, how many separate subnets do we need across the whole company? Third, what's the maximum number of hosts we'll need in the biggest single subnet? And finally, the sort of philosophical choice. Do we keep it simple and use just one size for all subnets?
Right. And figuring out the total number of subnets needed. That's where you really need to be careful. You can't just count physical locations or buildings. You have to count every single distinct network segment that needs its own address pool. So that includes every VLAN, those logical networks inside switches, every point-to-point serial link, those direct connections between routers, maybe over a leased line, and also any Ethernet WAN connections. You have to be thorough.
Okay, let's make that concrete. The example in the source helps here. Imagine a main office, a core site, with, say, 12 different VLANs, then maybe 3 branch offices, and each of those has 2 VLANs. And then you need connections, right? So 3 WAN links connecting all those sites together.
Okay, let's add it up. You've got 12 at the core, plus 6 across the branches, 3 sites by 2 VLANs, plus the 3 WAN links themselves. That comes out to 21. So your design needs to support 21 unique subnets right off the bat. And then for hosts per subnet, designers usually don't count every single laptop. They tend to work with profiles or archetypes like, okay, this is our standard large office size, maybe 200 hosts, and this is our small branch profile, perhaps 50 hosts.
Yeah, and the trap here, the thing people forget, I've seen this bite people, is the network gear itself.
Oh, absolutely.
Yeah.
Happens all the time. You must remember to account for the router's interface IP in that subnet. And if you manage your switches remotely, the switch's management IP too. Those static addresses are crucial.
Right.
Of course, the point-to-point WAN links are the easiest. They just need 2 addresses, one for each router interface at either end.
Yeah.
So if you see a subnet mask that allows exactly 2 usable hosts, like a 30 mask, you instantly know, that's got to be a point-to-point link. See? The design tells a story. Now, determining the size of the subnet, that brings in the math. A subnet mask essentially defines how many bits are reserved for hosts. Let's call that $. The total number patterns you can make with dollars is $2. But you can't use all of them for hosts. You have to subtract 2 reserved ones. So the usable host count is $2, $2, $2.
Okay, quick clarification. The two you lose are the very first number in the range, which is the subnet ID itself.
Correct.
And the very last one, the highest number, which is the broadcast address for that subnet. Neither can be assigned to an actual device.
Exactly right. So now we know we need 21 subnets, and our biggest might need 200 hosts. How do we decide on the size, the mask? Two main approaches. Option one size fits all.
Okay, this one sounds appealingly simple. The big advantage, clearly, is ease of management. Your IT team only has to learn and deal with one subnet mask across the entire organization. Makes things predictable.
It does. But the cost is potentially huge IP address waste. Let's say your biggest site needs those 200 hosts. So you pick a mask that gives you, what, 28 teles, 72 teles, and equals 200, 500, 4 usable IPs. Okay, great for that site. But then your small branch that only needed 50 hosts, it also gets a block of 254 addresses. And those WAN links needing only 2 addresses, they also get a block of 254. You could be wasting thousands, maybe millions of addresses internally.
Hang on, let me push back on that a bit. If we're using private addresses, like from RFC 1918, these aren't globally unique anyway. They stay inside the company. So does wasting internal private addresses really matter that much? Isn't the operational simplicity worth it?
That's a fantastic question. And it really hits the core philosophical debate in network design. You're right, wasting private IPs doesn't directly impact the global shortage. But it can seriously impact internal operations and future flexibility. Think about routing tables inside your own network. Huge, inefficiently allocated blocks can make those tables bigger than they need to be. And more importantly, what happens if your company merges with another one? It happens all the time. If both companies use the same massive wasteful scheme, say slapping 24 masks everywhere on the 10 network, you've got a massive IP conflict nightmare to sort out. Using space efficiently from the start makes everything cleaner, especially mergers.
Okay, free point. So what's the alternative?
Option 2. Variable length subnet masks or VLSM.
Right, this is the efficiency approach. Use different mask sizes for different needs. So the big office gets its 24 for 254 hosts. The 50-host branch, maybe it gets a 26, giving it 26 times 22, 2 equals 602 to our host. It's much tighter. And those WAN links get a tiny 30 mask, just enough for their 2 required addresses.
It's exactly. VLSM is pretty much the standard way things are done today. It just makes sense for conserving addresses. It's interesting, though, historically, VLSM wasn't always easy. Older routing protocols, like the original RIP version 1, they couldn't handle it. They didn't transmit these subnet mask info along with the route update. They just assumed the old class A, B, or C default mask.
Ah, so they couldn't tell the difference between, say, 172.16.1.024 and 172.16.1.026.
Precisely. It caused huge problems. It wasn't until modern classless routing protocols like OSPF, EIGRP, BGP came along. These protocols do include the mask length, 24, 26, 30, etc., and their updates. That's what made VLSM practical. This whole shift is tied to what we call classless interdomain routing, or CIDR, moving away from those rigid Class A, B, C boundaries altogether.
That history perfectly sets up the next big piece, the network address itself. Because before we choose the mask, we need the block of numbers to carve up. And this brings us to, well, arguably the biggest crisis in IPv4's history, running out of addresses. Address exhaustion.
Well, it was a huge problem, a disaster basically waiting to happen. The original internet design assumed everyone would get a unique public IP network block. But the pool of Class A, B, and C networks just wasn't big enough for the internet's explosion. By the late 90s, early 2000s, the writing was on the wall. INA, the global authority, handed out its last big blocks of IPv4 addresses back in early 2011. And AARON, the Registry for North America, officially ran out of its free pool by 2015. We were essentially out of new public IPv4 space.
Wow. So if we ran out, how did the internet keep expanding? How are new companies, new devices still getting online? What was the fix?
The lifesaver really was a combination of two things. Network address translation, NAT, working hand-in-hand with the private IP networks, defined in RFC 1918. This duo basically saved IPv4, giving it years more life than it should have had. NAT lets thousands, millions of companies all reuse the exact same private address ranges internally. So your company can use 10 0.0 door-to-door inside its network, and so can the company next door, and so can I at home. The NAT device, usually your router or firewall at the edge of your network, does the magic trick. It translates those common reusable private IPs into one, or maybe a few, unique public IPs, but only when traffic needs to go out to the actual internet.
Got it. So the private addresses stay private, and only the translated public address is seen globally. And these private ranges, the RFC 1918 ones, we see them everywhere now, right? Even our home routers use them. What are the main ones?
Yep, they're ubiquitous. There are 3 main blocks designated for private use. First, there's the single massive Class A block, 10.0.0.0 through 10.255.255.255. That's over 16 million addresses. Then there's a chunk of Class B space, 172.16.0.0 through 172.31.255.255. That's 16 contiguous Class B networks. And finally, the Class C range, 192.168.0.0.168.255.255. That's 256 Class C networks, often used in homes and small offices. It's interesting, surveys often show that something like 60 or 70% of large companies tend to use the 10.0.0.0 network internally just because it offers so much room for growth and flexibility.
And the benefits are huge, aren't they? It bought us time, delaying the IPv4 cliff edge. And it also helps the internet's core routers because ISPs just filter out routes for these private addresses. They don't need to know about every company's internal 10 network. Reduces routing table size.
Exactly. It's a clever workaround as long as you don't need every single device inside your network to be directly reachable from the outside internet without NAT getting involved.
Okay, let's tie this all together now. We've picked our network. Let's use that private Class B, 172.16.0.0. We did our homework. We know we need 21 subnets total. And our largest subnet needs space for 200 hosts. Now, let's try that first option. Design one single mask that works for both requirements. How do we find that mask?
Right. This is where the borrowing bits concept comes in. An IPv4 address is 22 bits long. Our starting point, 172.16.0.0, is a Class B. Traditionally, that meant 16 bits for the network part N and 16 bits for the host part H, so N16, H16. To create subnets, we need to steal or borrow some of those 16 host bits and dedicate them to a new subnet part. The fundamental rule is that the total number of bits must always stay 32, so N plus S plus H is 32.
Okay, so we're fiddling with the boundary between S and H. And the challenge is we need to find one boundary, one mask that satisfies two different needs at the same time.
Exactly. We have two constraints to meet. Constraint 1, for the subnets. The number of subnet bits, S, must be large enough that $2 is greater than or equal to the number of subnets we need, in our case 21. Constraint 2, for the hosts. The number of host bits, H, must be large enough that $2.22 is greater than or equal to the hosts needed in the largest subnet, in our case 200. Okay, let's work it out. We know N16 for our Class B. Let's figure out the minimum S we need. We need 21 subnets. Let's try powers of 2. 24 equals 16, nope, too small. $25 is $32. Okay, that's enough. So we need at least 5 subnet bits. Minimum is 5. Got it. Minimum 5 bits for S. Now for the hosts H, we need 200 usable addresses. Okay, let's try powers of 2 again, remembering the Unitas 2 part. $27 equals $128, $27, $26, $226. That's enough. We need at least 8 host bits. Minimum H8. Right. So minimum S5 and minimum H9. Oh, wait a second. If N16 and our minimum S is 5 and our minimum H is 8, that's 16 plus 5 plus 8 to 29 bits. But the address is 32 bits long. What happens to the other 3 bits? This combination doesn't seem to work if we have to use all 32 bits for N, S, and H. You've hit the key point of single mask design. Those are the minimums. If you're forced to use one single mask for the entire network, you have to find a combination of S and H that meets or exceeds both minimums. A and D uses up all the available bits, which is $32. In our Class B case, we have 16 6 bits available to split between S and H. We know H must be at least 8. Let's try setting H8. If H8 and N16, that S must be $32 and 16, 8 equals 88. So S must be 8.
Okay, so if we set H8 and S8, does that meet our minimums? Well, H8 gets 254 hosts, which is Ocal's 200. Check. And S8 means $28, 566 possible subnets, which is A equals 21. Check. And N plus S plus 8 plus 8 plus 8 plus 32. It works.
Exactly. For this specific problem, with the requirement of using a single mask, the only solution is N16, S8, H8. It meets both constraints and uses all 32 bits.
And translating that, 16 network bits plus 8 subnet bits means the dividing line is after the 24th bit. So in modern CIDR notation, we'd call this a 24 mask. The math forces that specific mask choice for the single-size design here.
Precisely. The requirements dictate the mask. #outro.
Okay, so once the engineer finds that mask, in our case 24, giving 256 potential subnets of 172.16.6.x.0, they'd usually list them out. Then comes the actual assignment phase, like, okay, 172.16.1.024 is for the main office LAN, 172.16.2.024 connects the servers in the data center, 172.16.3.024 is for that WAN link. Oh wait, no, a 24 would be wasteful there if we weren't doing single size.
Right. In a real VLSM design, that WAN link would get a 30. But in our single mask example, yes, it gets the 24 too. And good engineers are usually quite strategic about which subnet goes where. They might, say, reserve the first half of the available subnets, maybe 172.16.192.16.127.0 for all sites in North America, and maybe the next chunk, 128 through 191 for Europe. Why?
For route summarization. Grouping them geographically lets the main routers advertise just one big summary route instead of hundreds of small ones.
Exactly. It makes the routing tables much smaller, the network converges faster after changes, and it's generally more stable. Smart allocation matters. And then one last detail. Inside each subnet that's assigned, say 172.16.1.024, it's really good practice to carve up the host addresses. Maybe you decide addresses 0.1 through, say, 0.1100 are reserved for static assignment. Things like the router interface, 0.1 maybe, servers, printers, network devices, things that must keep the same IP. And then the rest of the range, maybe 0.101 through 0.254, that block is handed over to the DHCP server. That's the pool for dynamic addresses, laptops, phones, guest devices. Keeping them separate avoids chaos.
Yeah, prevents that horrible moment when DHCP accidentally hands out the IP address of your critical file server to somebody's phone. Definitely want to avoid that. So looking back, it really is all about balancing acts, isn't it? The whole design process is this trade-off between needing enough unique subnets, that $2 number, and needing enough usable host addresses in your biggest subnet, the 2H22 number.
It is. And that brings us maybe to a final thought for listeners to consider. We saw that VLSM, using different size masks, is way more efficient with IP addresses, no question. But arguably it makes life a bit more complex for the network team, who has to remember and work with multiple different masks. So here's the thought. We know public IPv4 addresses are basically a depleted global resource. We have to conserve them. Private addresses, less pressure, but efficiency still matters for internal reasons. When you're designing a network today, how much weight do you give to that operational simplicity of using fewer mask types versus the, well, almost ethical and technical need to use VLSM to conserve address space as much as possible, even internally? Where does that balance lie for you?